Right now, as you lie still and close your eyes, you are hurtling through space at nearly 500 miles per second. Not walking, not drifting, hurtling. The planet beneath you is spinning on its axis, orbiting the Sun, which is itself orbiting the center of the Milky Way, which is barreling toward a neighboring galaxy in a cosmic collision that has already been set in motion. You are not standing still. You have never once in your entire life stood still. And yet, when you look up at a clear night sky, everything appears calm, frozen, almost painted into place. The universe has a way of hiding its most extraordinary truths in plain sight. What you are about to hear is not fiction. It's not mythology or metaphor. Every single fact woven into this narration has been observed, measured, calculated, or theorized by some of the most brilliant minds our species has ever produced. And still, after centuries of science and thousands of years of stargazing, the universe remains almost entirely a mystery. We have mapped perhaps 5% of everything that exists. The other 95% is something we cannot see, cannot touch, and can barely describe. You are about to drift off to sleep on a pale blue speck of rock floating inside an incomprehensibly vast ocean of darkness, surrounded by wonders so strange they would seem impossible if they weren't true. Let's begin at the beginning. About 13.8 billion years ago, there was nothing. Not darkness, not empty space, nothing. No time, no matter, no distance between one point and another because there were no points. And then, in a moment so brief it cannot be meaningfully expressed in human language, everything that exists exploded into being. Scientists call this the Big Bang, though the name is somewhat misleading. It was not an explosion in the way we think of explosions, something bursting outward into an existing space. Space itself did not exist before that moment. The Big Bang was the creation of space, the creation of time, and the creation of all the energy that would eventually become star, every planet, every ocean, every living thing, every thought ever thought by any mind in the history of existence. It all came from a single point smaller than an atom. In the first fraction of a second after the Big Bang, the universe was unimaginably hot. Hotter than any star. Hotter than anything that currently exists in the observable cosmos. There were no atoms yet. No particles recognizable to modern physics. There was only a seething plasma of pure energy. Then, as the universe expanded and cooled, the first subatomic particles began to form. Protons and neutrons condensed out of that primordial fire. About 3 minutes after the Big Bang, those protons and neutrons began to combine, forming the nuclei of the lightest elements hydrogen, and helium. For the next 380,000 years, the universe remained a hot, opaque fog, too dense for light to travel through. Then, as temperatures dropped further, electrons slowed down enough to be captured by atomic nuclei. Atoms formed for the first time, and in that moment, the universe became transparent. Light traveled freely for the first time. That ancient light, stretched and cooled by billions of years of cosmic expansion, still exists today. We call it the cosmic microwave background, and it is essentially a photograph of the universe as an infant, visible to the right instruments in every direction we look. For hundreds of millions of years after that clearing, the universe was dark. There were no stars yet, no galaxies, just clouds of hydrogen and helium drifting through expanding space, slowly being pulled together by one force that operates patiently across any distance: gravity. This period is called the Cosmic Dark Ages, and it lasted until the first clumps of gas grew dense enough to ignite. Deep inside those clouds, pressure and heat built to a critical threshold and nuclear fusion began. Hydrogen nuclei were forced together with such force that they fused into helium, releasing enormous amounts of energy in the process. The first stars were born, and when they blazed to life, they ended the darkness forever. Those first stars were nothing like the sun you know. They were hundreds of times more massive, burning so ferociously that they lived only a few million years before exploding in cataclysmic supernova. In those explosions, the heavier elements were forged: carbon, nitrogen, oxygen, iron, gold. Every element heavier than helium that exists anywhere in the universe was created inside a star. The iron in your blood, the calcium in your bones, the oxygen in your lungs, with every breath you are taking right now, all of it was forged in stellar fire billions of years ago and scattered across space in stellar death. The Milky Way, the galaxy you call home, contains somewhere between 100 billion and 400 billion stars. That range exists because even with all of our technology, counting individual stars across 100,000 light years of space is not a precise science. Each of those stars is a sun. Many of them have planets. Many of those planets sit in what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a surface. When we consider that our galaxy is just one of an estimated 2 trillion galaxies in the observable universe, the arithmetic of potential becoming staggering. 2 trillion galaxies, each with hundreds of billions of stars, each stars potentially hosting worlds. The number of planets that might exist in the observable universe alone exceeds the number of grains of sand on every beach and desert on Earth combined many times over. And yet, from where you lie right now, you can see only about 9,000 of those stars with the naked eye on the clearest night in the darkest location on Earth. The rest are hidden by distance, by dust, by the brightness of our own galaxy's core, by the fundamental limits of human perception. Light from the farthest galaxies visible to our best telescopes has been traveling for over 13 billion years to reach us. When we look at those distant objects, we are not seeing them as they are. We are seeing them as they were when the universe was young. The most powerful telescopes ever built are time machines in the truest sense. Every image is a message from the past. Light travels at an approximately 186,000 miles per second. Nothing in the known universe moves faster. And yet, even at that speed, light takes about 8 minutes to travel from Sun to Earth. It takes over 4 years to reach the nearest star beyond our Sun, Proxima Centauri. It takes about 100,000 years to cross the width of our own galaxy. And the nearest large galaxy to ours, the Andromeda Galaxy, is 2.5 million light years away. When you look at Andromeda with the naked eye, which you can in the north hemisphere on a clear night, the pale smudge on light left its source 2.5 million years ago, before modern humans existed, before our ancestors had developed stone tools. You are seeing the deep past with your own eyes. Andromeda is not just a neighbor. It is a collision course. Both the galaxies are approaching each other at roughly 110 kilometers per second. And in approximately 4.5 billion years, they will begin to merge. This sounds catastrophic, but galaxy mergers are not the violent crashes you might imagine. Galaxies are mostly empty space. The stars within them are so far apart that even as hundreds of billions of stars swirl and intermix over millions of years, actual stellar collisions are extraordinarily rare. What will happen instead is a slow gravitational dance, a spiral and a merge across timescales too vast for any human context to hold. The result will eventually be an entirely new, larger elliptical galaxy. Astronomers have already given it a name, Milkdromeda. Our Sun sits about halfway out from the center of the Milky Way, on a minor arm of the galaxy's spiral. It has been orbiting the galactic center for its entire existence, completing roughly 20 complete orbits since it formed 4.5 billion years ago. One full orbit of the galaxy is called a galactic year or a cosmic year, and it takes approximately 225 millions of years to complete. The last time our solar system was in the same position in the galaxy as it is today, the earliest dinosaurs had not yet appeared. 2 galactic years ago, multicellular life had barely begun. The Sun is a middle-aged star, roughly halfway through its 10 billion years lifespan. In about 5 billion years, it will exhaust the hydrogen fuel in its core, and expand into a red giant large enough to engulf Mercury and Venus and possibly Earth, and then collapse into a dense, dim remnant called a white dwarf. The story of our sun is not unique. It is one chapter in a story told by every star. Black holes are perhaps the most dramatic characters in that story. When a star, much massive than our sun, dies, it does not simply expand and cool. It collapses under its own gravity with such force that the core compresses into a point of infinite density called a singularity. The gravity around this singularity becomes so extreme that nothing, not even light, can escape beyond a boundary called the event horizon. This is a black hole. From the outside, a black hole appears simply as a region of utter darkness, detectable only by its effects on nearby matter and light. Stars orbiting near the center of our galaxy move at speeds that only something extraordinarily massive and compact could explain. At the heart of the Milky Way sits a supermassive black hole called Sagittarius A star, with a mass of 4 million times that of our Sun compressed into a region smaller than our solar system. Supermassive black holes exist at the center of virtually all large galaxies. Some of them are truly monstrous. The black hole at the center of the galaxy Messier 87, which became the first black hole ever directly imaged in 2019, has a mass 6.5 billion times that of the Sun. If you place that black hole at the center of our solar system, it would swallow everything out past the orbit of Pluto and well beyond. And yet, there are black holes even larger than that. The largest known, a quasar called TON 618, contains approximately 66 billion solar masses. 66 billion suns compressed into a singularity. Numbers like this exceed not just human intuition, but human imagination. They belong to a scale where language starts to fail. And yet, the universe is not just vast. It is also almost entirely empty. If you took all the matter in the observable universe and spread it evenly through the space it occupies, you would get roughly 6 atoms per cubic meter. 6 atoms in every cubic meters of space on average. The stars, the planets, the gas clouds, the galaxies themselves are just rare clumps of concentration in an otherwise almost perfectly empty void. Even the atoms that make up solid matter are themselves almost empty. An atom is primarily space. If you enlarge the nucleus of a hydrogen atom to the size of a golf ball, the electron orbiting it would be roughly 2 miles away. Everything between the nucleus and that electron is empty. When you press your hand against a wall and feel resistance, you are not actually touching the wall. The electromagnetic forces of the electrons in your hand and the electrons in the wall are repelling each other. You have never in your life directly touched anything. This leads to one of the most unsettling realities in all of physics: the quantum world. At the smallest scales of reality, particles do not behave like tiny balls obeying ordinary rules. They exist as probability waves smeared across space, occupying no single definite location until the moment they are observed or interact with something. A particle can be in two places at once, travel through paths simultaneously, and influence another particle across any distance instantaneously. This last phenomenon, called quantum entanglement, was so strange that Albert Einstein dismissed it as impossible, calling it spooky action at a distance. Experiments since then have confirmed it beyond any doubt. Two particles can be connected such that measuring the state of one instantly determines the state of the other, regardless of whether they are side by side or separated by a billion light years. The universe at its deepest level is woven together in ways that defy ordinary cause and effect. Einstein himself revolutionized our understanding of space and time in ways that still feel dreamlike. In his theory of general relativity, he described gravity not as a force between objects, but as a curvature of space-time itself. Mass tells space-time how to curve, and curved space-time tells mass how to move. The Earth does not orbit the Sun because the Sun is pulling it. The Earth follows the most natural path through a region of space-time curved by the Sun's mass. This was proven definitely during a solar eclipse in 1919, when astronomers observed that light from distant stars was bent as it passed near the Sun, exactly as Einstein had predicted. Space itself bends around massive objects, and if space bends, time does too. Time does not pass at the same rate everywhere in the universe. The closer you are to a massive object, the slower time moves for you relative to someone farther away. This is not a thought experiment or a metaphor. It is a measured, confirmed physical reality. The GPS satellites orbiting Earth experience times at a slightly different rate than clocks on the surface. Engineers must account for this relativistic time difference in their calculations, or GPS coordinates would drift by miles within a single day. If you stood at the edge of a black hole's event horizon, time for you would move so slowly relative to the outside universe that the entire future of the Earth might unfold in what felt like moments to you. Time, the thing we feel most certain about, the steady drumbeat of existence, is elastic. It stretches and compresses depending on where you are and how fast you are moving. Beyond black holes, general relativity predicts the existence of other exotic phenomena. Neutron stars are the collapsed cores of massive stars that did not quite have enough mass to become black holes. They are extraordinarily dense. A teaspoon of neutron star material would weigh approximately 10 million tons. The fastest known neutron stars, called pulsars, spin hundreds of times per second, beaming jets of radiation into space like a cosmic lighthouse. Some neutron stars are paired with companion stars, slowly devouring them, accumulating matter until they trigger spectacular thermonuclear explosion on their surface, briefly becoming millions of times brighter than the Sun. These are called novae, and they are visible from other galaxies. There are also objects predicted by the equations but never yet observed. Wormholes. Solutions to Einstein's field equations suggest that if space-time can curve, it can potentially curve so much that two distant regions of space or even two different moments in time could be connected by a shortcut. A wormhole or Einstein-Rosen bridge would theoretically allow passage from one point in the cosmos to another without crossing the enormous distance in between. Whether such things can actually form and remain stable long enough to be useful is still deeply uncertain. The equations allow them. Reality may or may not cooperate. Then there is the deepest mystery of all, the thing that keeps cosmologists awake at night, so to speak, which is fitting given where you are headed now. When astronomers observed the expansion of the universe in detail, they made a discovery that should have been impossible. The expansion of the universe is not slowing down, it is speeding up. This is extraordinary because after the Big Bang, the expansion should be decelerating. Gravity pulls matter together. Over cosmic time, the collective gravity of all the matter in the universe should be applying the brakes to that primordial outward motion. Instead, something is pushing the universe apart with increasing force. Whether it fills all of space uniformly, it has no mass, it emits no light, and it cannot be detected by any instrument we have ever built. We have named it dark energy, and it makes up approximately 68% of everything in the universe. Then there is dark matter, distinct from dark energy and equally invisible. When astronomers measure the speed at which galaxies rotate, they find something strange. The outer edges of galaxies rotate far too fast. Based on the visible matter alone, the gravity holding galaxies together should not be nearly strong enough. The stars on the outer edges should fly off into space. They do not. Something invisible, something with mass, something that interacts gravitationally but not with light, must be threading through every galaxy, providing the additional gravitational glue that holds them together. This is dark matter, and it makes up approximately 27% of the universe. Added to dark energy, that means roughly 95% of everything that exists is completely invisible, undetectable, and essentially unknown to us. Everything we have ever seen, studied, touched, or built, every star, every planet, every ocean, every atom, every photon of light ever absorbed constitutes a mere 5% of reality. We do not know what dark matter is. We do not know what existed before the Big Bang, or whether the world before even has meaning in that context. We do not know whether our universe is the only universe. The theory of inflation, which describes How the universe expanded at extraordinary speed in the first fractions of a second suggests that different regions of space expanded at different rates and into different conditions, potentially giving rise to an enormous, possible infinite number of separate universes, each with its own physical laws, its own fundamental constants, its own version of reality. Some of those universes might have slightly different values for the forces of physics, making atoms unstable, or stars short-lived, or chemistry impossible. Our universe seems extraordinarily fine-tuned for the existence of complexity, chemistry, and life. Whether that is the result of a cosmic lottery, a selection effect in a multiverse, or something else entirely remains one of the deepest open questions in all of science. And what about life? We know it exists here. We have no confirmed evidence of it anywhere else. Yet, the chemical ingredients for life, water, carbon, nitrogen, the amino acids that form proteins, have been found in deep space, in interstellar clouds, in meteorites, forming spontaneously through chemistry alone. Organic molecules have been detected in the atmosphere of Titan, one of Saturn's moons. Liquid water almost certainly exists beneath the icy crust of Europa and Enceladus. Mars shows geological and chemical evidence of having warm and wet billions of years ago. The ingredients appear to be common. Whether the leap from chemistry to biology has occurred elsewhere or occurs easily wherever conditions allow, or whether Earth is an extraordinarily rare accident, we genuinely don't know. The universe is approximately 13.8 billion years old. It will continue to exist for timescales so vast that our numbers start to feel meaningless. In about 1 trillion years, the last star will have burned out, and the universe will enter a long, dark era of cooling silence. The black hole slowly evaporating, matter dissolving into radiation, entropy claiming everything that ever was, and yet here we are, near the beginning of all of that, on a small, warm planet around an ordinary star in one of hundreds of billions of galaxies, asking questions that the universe itself may never answer. That might be the most remarkable things of all, not the size, not the age, not the incomprehensible scales of space and time, but the fact that some small part of this universe became curious about itself. Whether we are alone in that curiosity or one voice in a vast and silent chorus we have not yet learned to hear, remains the open questions for our existence. We are, at minimum, proof that the universe can wonder, and perhaps that is where every great journey begins.